Yes, hopefully it has started. Yeah, so please remind me if I forget. Okay, so as I said, we have to come back to similar diagram again and again. So let's look at some of the basics before continuing to the next slide where we left off yesterday. The first thing is this memory location. So I'm considering this memory location instead of a microcontroller because there are certain dependencies which come from external components on the microcontroller chip. Okay, so this is 80C51 is a microcontroller. All these intermediate chips are the interfacing electronics, as we discussed over here, interfacing electronics. And within the interfacing electronics, there is a memory chip called random access memory. So this is a type of RAM which is used over here. So this 6264 is the number for this. So let's look at it. So all those address, memory, and control. So also we had discussed yesterday. So I will. So we had discussed this diagram that any computer must have address bus which is unidirectional, must have a data bus which is bidirectional, and also a control bus which is unidirectional, same as address bus but different in functions. Okay, so these are the three buses that we discussed yesterday. So now coming to this diagram, where are those buses? Okay, so which ones are those buses? So we explained that A some number represents address bus, D some number represent data bus, and just names or some other types of lines are called as control lines. But why and how we are going to use all three categories of buses, address, data, and control. So that's what is shown here. Look at the pins inside U2, which is IC number 2, which is a memory chip 6264. This is a static random access memory, is called SRAM. So static dynamics, so those are different details you will possibly study in VLSI engineering course. So I'm just skipping it. So this is a static RAM which forgets its data if I turn off the power. So power lines are not shown. It is assumed power supply like 5 volt and ground are already applied. But here only the main connections are shown except the power. So A0 to A12 are representing the address lines. So that means 2 to the power 13 number of memory locations will be present inside this chip. So this is an important information. So A0 to A12 are the address lines. D0 to D7 are representing data lines. And all remaining 4 lines, which are chip enable, chip select, write enable, output enable. So these are the names. Don't remember the names. Okay, for now, don't remember the names. Just understand that these are the control lines. So there are 4 control lines, 8 data lines, and 13 address lines. So address lines are always unidirectional and they are entering. So arrowhead is not shown. They are all entering from the microcontroller and entering inside the RAM chip. So these are all input to the RAM chip, output to the microcontroller chip. And data lines are bidirectional, as I said. So that means each of those D0 to D7 are representing 2 directional or bidirectional lines. So that means you can send data inside this U2 or you can take data from U2 to and take it out to the microcontroller. Okay, so that is bidirectional function for this data lines. And this control lines with all these different names are again unidirectional lines. They are always entering the U2 chip. So they are output from the microcontroller or any other circuit, but input to this memory chip. So this, why I'm saying this, because our next slide is actually related to this information about this address, data, and control signals. Okay, so now I'll go where we left off. So we ended up with this particular slide yesterday, and we will continue from this point onwards. Okay. So these are read, write are the control lines D7 to D0. So here I'm considering most significant bit first until least significant bit. So that's why D7 to D0. Same thing for address A15 to A0. So that means there are 16 address lines. There are 8 data lines. Out of 16, we were using 13 for those RAM. Okay, so previous diagram in the calculator, we were using only A12 to A0, but there are A13, A14 and 15 as well. So 16 address lines are coming out of the microcontroller or the microprocessor. Now, is the diagram that we should start understanding very clearly. This is very important diagram. This is a called as timing diagram. Timing diagram is nothing but a time domain representation of multiple digital signals. So I'll repeat, timing diagram is a way to represent multiple digital signals in a time domain representation. So it is not a frequency domain. This is only strictly time domain way. But in the circuit, you have seen previously, there are so many connections, so many address lines, so many data lines, and also a few control lines. So how do we represent their interaction with time? So how they are correlated, how they are interrelated with time, because timing is very important in any digital circuits, especially sequential digital circuits. And microcontrollers are typically, or rather I'll say mostly, most part of the microcontroller represents a sequential operation, so something like which is sequenced with clock, which is synchronized with clock. So sequential circuits always have a clock signal. So that is the basis, and clock signal is shown on the top diagram. So let's understand this top, how do we represent timing diagrams in this form. So clock is this is a digital clock signal. That means this lower side represents 0, logic 0, and the upper side represents logic 1. And this clock has one cycle, which is very intuitive, and there are many clock cycles shown over here. So every clock has a logic 1 duration and logic 0 duration. So x-axis is time for all these waveforms, but y-axis is logic level. Instead of voltage, we are representing logic level, because in digital circuits we follow that strategy. So whenever you see this as logic 0, and whenever you see at the upper side but connected, you can consider it logic 1. But clock is just a single line signal. So you can say that this clock is internal. Now, where I had shown the clock in that diagram that I showed earlier in the calculator, it is very important to understand. See, here in this particular diagram, the clock signal is not explicitly shown like power lines, like VCC, ground are not shown for all these chips. Similarly, clock signal is actually not shown. In fact, that clock signal in the timing diagram is somewhere inside this microcontroller chip, somewhere inside. So again, we will go in detail where is that clock signal inside, but it is related to this external signals. We will discuss that again once we go to further details of 8051 microcontroller. But clock is the signal which is controlling all these functions, right? Every function is synchronized with that hidden clock inside the microcontroller that is not shown in this particular diagram, but very important and unavoidable. You need to have a clock signal. Okay, so in the timing diagram waveform, in the timing diagram, it is basically shows multiple waveforms of digital signals, and the second line is the address k-1 to 0. That means, let's say, A15 to A0. So there were 16 address lines, up to 16 address lines for the microcontroller, but 13 address lines for the memory chip that I said. So assuming all 16 are shown, but if you draw 16 lines similar to clock, it will be very cluttered diagram. It will be very confusing diagram. So instead, so people have thought that why not we represent that address with some hexadecimal value, something like as I wrote S and D at the beginning of the class. So similarly, you can say that the S must be having some value, right? Some 8-bit value or some 16-bit value or even 32-bit value or even any other number of bits value. So that value can be represented and just combined together. Instead of writing or drawing 16 different signals similar to clock, we can actually have a merged signals, something like this. And this, you have to understand the syntax of drawing this kind of things, or the rules of drawing timing diagrams. So whenever you say you see this both the lines, let's say logic 0 and logic 1 simultaneously, that means it represents a group of signals. That means it represents a bus, a little bus or large bus, whatever number of lines. So there are more than one lines represented by using this kind of dual line representation. So this is neither 1 nor 0, but it's some number which is combined together between A15 to A0. Okay, now this dashed portion or the shaded portion represents don't care signal or don't care value. So whatever value this 16 bits of address may carry during the first clock cycle is not relevant, is not useful. So that's why these are don't care condition. So don't care condition you must have read in digital electronics. So this don't care condition is shaded condition. But whenever you show this with white space in between these two lines, that means there is a valid 16-bit number. That valid 16-bit number is called as write address or read address or any other type of address. So some valid address is there if there is a white space in between this upper and the lower lines representing multiple data, multiple address lines. Okay, so again, after certain clock cycle, there is a don't care timing where you are ignoring whatever is there in the address bus. And later on, you can have another address. Now this read and write address, all this can be basically all various different 16-bit numbers. So write address, there could be two write address side by side. There could be two read address side by side. There could be read address first, then write address. So all combinations are possible. But whenever you see this white space in between, that means valid value of address or data or any other value is present, which is useful and valid. Now this bus enable is another single bit or single line or single connection wire which represents a digital signal similar to clock. So clock is a single line, address is multiple lines because it's a bus. So bus enable could be another single line similar which is represented under control signal. So this is a type of control signal. Clock is a control signal. Address is an address, obviously address bus, as I said. Read/write bar. So this is another single line. So that means you don't see this upper and the lower lines. So read/write bar is another control line which represents, if it is 1, logic 1, it represents read. If it is logic 0, as over here, so this is write. So here, look at this. Write address is synchronized with this write bar signal. So this is logic 0 signal. So that means whatever address is there, so that is used to write a signal. So write means you wanted to store a data, right? And read means you want to fetch a data or you have to copy a data. So that is read operation. For read operation, you need to have logic 1 as you see over here. So during the read address, whenever it is applied, you are also applying R signal, that is logic 1 signal. So our W bar is ignored over here. Okay, and bus enable is, you don't see any bar over here, so that means it is active high signal, active high digital signal. So bus enable means whenever you are writing address, write address is coming and you are enabling the bus. So that means your address data, all other buses are enabled. And once you enable the bus, then you can do read, write or whatever operation. So during every write operation, you are keeping the bus enable 1. During read operation, again you are keeping the write bus enable 1. So that means reading is allowed only after this age and before this particular age. So that means whenever bus enable is 1, then only your writing or reading is applicable or valid. Otherwise, it is not valid. Only address doesn't make sense. Only clock also doesn't make complete sense. So you need synchronized signal. So when you have to apply a clock, at the same time you have to apply a write address. At the same time, you also have to apply this bus enable to be logic 1. At the same time, if it is write operation, you have to keep this write bar to be 0. R/W bar to be 0. So this is how, this is time correlated signals. Okay. Similarly, there could be byte enabled signals. So byte enable is not present everywhere. So it could be 1 bit or it could be multi bits. Similarly, the data bus is represented over here. So this is a generic example, as I said. So data bus could be 8-bit, as we had seen in the calculated diagram. But data bus could be 32-bit, data bus could be 64-bit, data bus could be 16-bit. So, or even 8 bits that we had seen earlier. So write data, so D15 to D0 or D7 to D0, whatever is the width of the data bus. So that represents a data operation or data transfer operation with a, that means there are 16 lines over here. That is 15 D15 to D0. There are another 16 lines. So there are 16 lines here. There are 16 lines here, and there are other lines you can just count on. So for write data, so you have to give a write address. You have already given a write address. Now you have to synchronize the data along with the address. So that is another requirement. So not just address and control signals like bus enable read write bar, but also data should also get synchronized, in time synchronized along with the address and the clock and other control signals. So write data is available. So whatever data is present over here in this write data D15 to D0, that will be copied or written to the address location that is represented over here. Okay, so if some concept is not clear so far, I'll take very specific examples to tell you more about this write and read address and data signals. Now, acknowledge is again not always present, but in certain cases acknowledge is present. That means you have written a data, and after you have written a data, you want to know that whether your writing process is successful or not. So that means if your memory is disconnected, so your writing attempt will fail. So if you don't plug in your USB, let's say memory stick to your computer, and you are trying to transfer data, automatically your computer will give you an error signal, right? That your device is not plugged in or that drive doesn't exist. So that happens due to this acknowledgement. So whenever your read or write operation is there, so you must take an acknowledgement that it is successful or not. So logic 1 pulse means successful. Logic 0 means either waiting or not successful. Again, the data bus could be splitted into two parts. Inside the microcontroller, this thing happens, not outside. Actually, you get to see this, but inside the microcontroller. So I said data bus is a bidirectional bus. So for write operation, data bus is an output bus. For read operation, data bus is an input bus. So it happens inside the microcontroller or inside the microprocessor. So read and write data are separately shown over here. So here read data is another 16-bit data bus, and read data is only applicable whenever the read signal is there. That means R is logic 1, and you have applied bus enable, you have applied some clock signal. At the same time, you have applied this is at the same time. This is, so your acknowledgement comes by synchronizing with the acknowledgement. You can actually read the data. So this timing diagram is a generic diagram, as I said. So the timing diagram for a given processor, let's say 8051, will have slight difference with ARM. It will have slight difference with AVR. It will have slight differences with other microcontrollers. Okay, but the concept over here that I'm trying to convey is that you have to time synchronize many signals, all the signals, in fact, corresponding to control lines, data lines, and address lines or buses. You can call it address bus, data bus, and control bus must be synchronized with each other in time. So if you desynchronize the signal, it doesn't make sense. So actually this diagram is representing one signal for clock, second bus, third, fourth. So these are the control or status signals. So 4 plus, let's say 16 plus 16 plus 16 plus 2. So there is 16 plus 16 plus 2 plus 4. So this many number of whatever the total sum is coming. So that number of digital lines are represented by using this simple one-page diagram. So it is actually very simple if you have a little practice of using and reading this kind of diagrams. Okay, so this timing diagram is absolutely unavoidable in any digital systems that you'll work in your entire life. I can tell you to this extent that any digital systems, if you are working in depth with design and with development of hardware as well as software, you have to basically go deeper to this extent where you have a very clear understanding how the timing is synchronized for address, data, and control signals. Okay, so assuming all the signals are the power signal is always applied. So power must be present during all this operation. If you cut the power supply, obviously you do not have any value, any use for this kind of timing diagram. So power is always on, which is again not shown. Okay, so any question over here, because this is very important topic. Okay, so I'll go to the next slide. Yeah.
So the write data and read data, they are physically the same bus or different.
Yes, they are physically the same bus outside the processor, as you can see over here. So this data lines, so if you see D0 to D7, ignore the A part of it. So D0 to D7 in this diagram. So this is just a bidirectional data bus, but inside the processor, that data is maybe splitted into two parts, read and write buses, two separate buses for certain microcontrollers. It doesn't happen for 8051, but for ARM and other advanced microcontrollers, such splitting. So this data write bus and data read bus are physically separate inside the chip. Inside, outside the chip, they may be different, they may be same also, something like this bidirectional bus. Okay, so we'll continue with our slides. Okay, so so next few slides we have already discussed several points. It's just an iteration, just for you to have a note down of the facts in the form of slides. So address bus is used for both memory and I/O devices. That means input-output devices also require address bus. Memory requires address bus. Also, different types of memory require separate lines or separate values of address, and this address bus can be shared actually. That means you can have a one single address bus going to both memory and I/O devices, and the same address, but the value of the address determines which one you are selecting, and every address must be unique. Okay, so that is another requirement, such that it can be easily recognized by whichever memory or I/O or any location inside memory or I/O device. And the CPU puts the address bus on the puts the address on the address bus, and the decoding circuitry finds the device. Okay, so this decoding circuitry is very interesting. So there are interesting types of decoders which are slightly different than the standard decoders, and also mostly they are similar than standard decoders. But this decoding circuitry plays a very important role in the addressing operation. That means we'll discuss again in further detail as I go to the memory section. Then the data bus, the CPU basically transfers data through the data bus. I think it is very clear by now. And the control bus basically controls whether it is read operation or write operation or some clock operation, or basically is enabling operation, disabling operation. So those kind of control signals are used or connected through the control bus. Now, there are certain basic rule of thumb that we may consider, and most of them are valid for a majority of the cases, I will say, based on my experience in the past. So the more data buses available, the better the CPU. See, the write bus and read bus was shown separately on the timing diagram. What does it mean? You can have simultaneous read or write you if they are separate physically. Okay, but we were not using them simultaneously as it was shown in the timing diagram. So whenever write was operating, read was off, and whenever read was there, write was off, using R/W bar pin that we discussed. But technically, if you have multiple data buses, let's say separate one with separate read and write control, if we have the separate control over different data buses, it is definitely better, because it's like a highway lanes, right? So if you have more lanes, that means more vehicles can be accommodated and people can move fast, whether it is buses or simple carts or scooters or buses. So more lanes are always better, but more lanes comes with a cost. You need more investment, you need more space, and so on. And more buses means more expensive CPUs and computers. So that means your buses will definitely increase speed if you have more of them, but your cost may not be very economic. So there should be a compromise, there should be a perfect balance between your requirement and the kind of space that you're using for your data buses and the complexity of the circuit. So here typically it is very true that the average size of data buses in standard CPUs range between 8 to 64 in general, but there are wider data buses. Smaller data buses are not present these days in commercial CPUs or microcontrollers. 8 is the minimum, but 64, 32, 16 are all very common values for the width of the data bus. As I said, for the RISC, so I was showing 24 bits, right? Move S and D all side by side for RISC. So such thing is possible if you have a wider data bus, wider basically way to transfer data. More number of bytes can be transferred side by side. So if you can do that, not just in RISC and CISC, but also in memory accessing, it helps a lot, as I described. And data buses are typically bidirectional, but if you have separate read and write data buses, then each of those buses are unidirectional. You have to understand this. So if you have separate read and write data buses, they are unidirectional individually, but in general, data buses are bidirectional in standard embedded CPUs, because to reduce the number of lines coming out of the number of pins coming out of the chip. And the processing power of a computer is definitely related to the buses, as we have seen in the RISC processor. So we are inviting or transferring 3 bytes at a time, side by side. So that means obviously the processing power is improving. So what do I mean by processing power? For the same power consumption, can I reduce the timing? So that means my processor or my computer becomes faster. So that's what I mean. So I have a powerful CPU. So what do I mean by that? My CPU is faster than others, right? So that's what is processing power of a computer is related to the bus sizes. Now, more address buses might be available, but the larger the device, if you have a large number of devices, or let's say large memory. So suppose you must have seen while purchasing a smartphone, some people say that it is 8 gigabyte, or some people say that 16 gigabytes, some people only say 4 gigabyte or 2 gigabytes. Why it is so? Because that number of gigabytes not just depends on the memory size, but that also depends on how much your processor can address, can handle. So how big a memory your processor inside the phone can handle. So that means more address buses or more address lines are available for more powerful devices and vice versa. So more the address lines, that means more larger memory you can access, larger memory you can connect and use with your phone or any embedded system. A phone is actually an embedded system if you look at it very carefully. So we'll discuss again in due course of time. The number of locations in which a CPU can communicate is always equal to 2 to the power x. So that means where x is the number of address lines. So if you have 16 address lines, let's say x equal to 16, then 2 to the power x, which is 65,536. So you can calculate that. So it is very standard value, which is that's why I'm remembering. Otherwise, I'm not mugging up these values. Okay. So if the x is 8, then you can have 256 locations, 2 to the power 8. If x is 16, 2 to the power 16 memory locations can be accessed or can be read or write by a given computer or CPU, central processing unit. But the number of address lines is actually independent of the size of the data bus. You have to add another thing, address and data buses are different. So your data bus may be 8 or 16, that doesn't make any relevance with the number of address lines, no connection as such. But address lines are related to maximum memory or IOs that it can handle in in operation. So if the CPU with 24 address lines and 16 data lines can provide a total of 2 to the power 24, so that means 2 to the power x is 24 or 16 megabytes. So this is an example. So you can increase the value of x, go to giga, you can again increase it further, you can go to terabytes. So that means our desktop PCs or laptops support terabytes of memory. So that means they have more number of address lines. So uh, that's the fact inside any processor or any computer system. For embedded system, we don't need terabytes in general, but we need relatively less. So that's why we stay with megabytes most of the time at max. So at each location can have a maximum of 1 byte of data. So typically, as I said, that each location of a memory typically has 1 byte of data. That means only 8 bits data can be stored in a given location. But as I said, in the RISC example, if you remember the RISC example I was explaining first. So here, there you can arrange bytes side by side. So that is an exception which is possible. That means although each location typically stores 1 byte, but you can extend it by keeping the lines side by side or the locations of the memory side by side, such that each byte can access more than 1 bytes of data. So this is basically a little additional point that I wanted to describe. For 8051, the maximum is only 1 byte of data for every location. For ARM, this is not true. Maximum is actually 64 or 32 bits. It depends on which mode of ARM or which ARM processor you are using. Okay, so this maximum of 1 byte of data for each location is only for 8051. Okay, and then all general purpose CPUs have byte addressable. So general purpose embedded CPUs, should I mean. So byte addressable, that means you can access 1 byte at a time, like 8051. For the CPU to process information, the data must be stored in some memory. And the memory may be volatile memory such as RAM or non-volatile such as read-only memory or flash memory. Okay, which is referred to as primary memory. So primary memory is typically the read-only or memory or flash memory. So read-only memory provides information that is fixed and permanent. That means you don't change your operating system. So it is kind of fixed, you can say. So earlier it was absolutely fixed, and these days it is, you can say, in principle fixed. Because in principle, because I can update my fixed operating system on my phone or on my computer. Okay, so that's why the read-only memory or the flash memory provides a permanent storage of the data, or I can say that until I format that. And there are several ways to initialize the data. So basically, once you store the data, first of all, you have to keep a track of data. Suppose you have 1000 songs stored in your mobile phone. How do you keep track of that? So where exactly, which address location, which song is stored? So that is taken care by the operating system automatically in the background. So that's why we need operating system. So the operating system in any embedded or any computer based system, general purpose even, it maintains certain list or it maintains certain tables where it actually stores the account of every data segments or data chunks. Let's say song one, so it takes, let's say, some few megabytes. So those few megabytes are actually entered, the starting location and the ending location are entered in some table which is hidden. So that is the embedded system. In embedded system, we maintain those hidden tables inside the operating system or through the operating system, and those tables indicate where exactly which data is present. So it keeps a track of which data at which location, at what location. Then RAM, on the other hand, stores information that is not so permanent. Basically, we don't store operating system in RAM. right? So we only store runtime data or the real-time operation related data in the RAM, because after closing or powering off, the RAM will forget each and every data. Okay. So various versions of operating systems, OS means operating system, I'm meaning here, and application packages are actually using RAM because they actually ROM takes longer time to access relatively as compared to RAM. So in high-end embedded systems, so the part of the program is read once you start a program. So once you start a phone or a computer, it takes certain time to boot up, right? You must have seen you have to wait for some minutes or seconds at least these days to boot up. So during the starting up process or booting up process, the operating system code is actually read from the ROM and stored in the RAM. So whether it is flash ROM or any other ROM, so it is read from there and stored in the RAM. And larger the RAM is better because it is faster. It will give you more space to handle, so you don't have to go back and forth with ROM. So if you have small RAM, why the system is slow? Have you asked this question to anyone? So the answer is that if your RAM space is small, then you have to go back and forth to ROM again and again, and ROM accessing is slow, relatively slow. It's not very slow, but relatively slow. And then if you are accessing the slower memory, and that means you are wasting time. As a result, your system will slow down. So if you increase RAM, you automatically have large space, so you can store everything from the ROM, at least the part of the operating system or the codes, and then you execute from the RAM, and automatically your system becomes fast. Okay, so that's what I've written. The CPU gets information to be processed first to the RAM from the ROM, and if it is not there, then it has to directly go to the ROM all the time. So if you don't use the RAM for storing the program, it is not necessary that always we have to use the RAM for storing the program. So if that's why you can directly process everything from ROM. So in standard embedded system like 8051 system, we actually don't copy the code from ROM to RAM. We actually directly read from the ROM space, and then if some data is there, then we go to the RAM. So I was talking about program memory and data memory at the beginning while explaining CISC and RISC today. So the program memory is ROM and the data memory is RAM. Okay, so these are the memory utilization. So you have to judiciously decide which is the better option. So in standard 8051 system, program memory is always a flash or ROM or any other types of ROM, and data is in RAM or registers inside the microcontroller. So you can actually consider ROM as a primary memory and RAM as a secondary memory. So typically, this is another way of looking at things. So primary memory stores fixed kind of data, and secondary memory stores temporary kind of data like RAM. Now, so as I said, I'm talking too many things about memories instead of directly going to the microcontroller. So there is a reason behind why I'm doing so. Because you have to understand why those microcontrollers came and what is the logic behind those design. Is it that some companies or some people have designed and we are just reading them? No, it's the objective is something bigger than that. You have to understand how those things came into existence, what was the logic, and what could be the logic in the future, such that you can even work in these digital systems while developing different microcomputers. Okay, so these days microcomputers are so small, having so powerful memories, and it is very closely linked to memories. So you have to understand a little bit about memories. We'll not go deeper, but some basic facts must be understood, and you have to grasp those facts. Then only you can understand microcontroller with confidence. Then there will be flawless understanding. You know some basic definition of memory, so I'm not going to it. Memory is a collection of data program, data or program storage. So usually storage location holds 1 bit, but in most of the memories we are actually grouping into a bunch of 8. Okay, 8 bits. So that's one 8-bit, 1 byte, one set of 16 bits or 2 8 bits, one word, something like that, and then long word 32 bits and so on. So those kind of these 8 storage locations, basically, let's say I have 8-bit memory, that means all side by side. So this 8 storage location can only be accessed together. So that means I can access 1 byte of data simultaneously. Similarly, I can also access 32 bytes of data simultaneously, as in RISC processors. I can access other 64-bit data also simultaneously. That is also possible. But this concept originally was very popular with 8-bit and also adopted in 8051, AVR kind of microcontrollers. So one can only read or write in terms of bytes to and from memory at a given time. Okay, so while you are writing something to a memory location, you cannot read at the same time point. You have to wait until next few clocks and then you can do the reading. So either read or write is possible at a given time, whether it is group of 8 or group of 16 or group of 32 or any other group of bits. And you know, memory is measured in kilo, mega, giga, tera, basically, and these are the standard ones for conversion. This is just for reference, so we won't go in detail. Now, more importantly, these memories are how they're closely related to program and data in any embedded systems. This is something you must get this point from multiple directions. So that's why I'm coming here. So while a program, so what do we mean by program? Is set of instructions. That means there are some set of commands. Is a program organized in a certain logical manner. So while a program is entered into a computer or stored, it is actually going to the memory. So that memory is the program memory, and program memory is a ROM kind of memory or flash kind of memory, and this ROM flash comes under non-volatile kind type of memory. Okay, so this is important. So program is typically stored in flash or ROM, which is a non-volatile memory. Then as the microcontroller or a processor, because I'm talking inside the microcontroller, there is a microprocessor. So when the microprocessor starts executing the instructions, it brings the instructions from the memory to the microcontroller or processor itself, but in a sequential manner, one by one. Okay, so the memory is storing the 3 locations, move, S, D, that example that I said today. So those 3 things, if they are sequentially arranged in one after another in CISC processors, so they must be fetched one after another. That means one by one. First, you have to go to the first location, read. Okay, now once you have reading is complete, go to the second location, do the same reading from the second location, then go to the third location. So one at a time. And memory is also used to hold data, as I said. So for data, we can store like songs in the flash memory. Okay, so once we store the song, it should not get forgotten. So we should be able to play it next time after we restart the phone. So that's why data could be in non-volatile memory. Data could also be in the volatile memory during playtime. Let's say I'm playing a song from my phone, MP3. That song is coming from the volatile memory to the from the non-volatile memory to the volatile memory. That means from ROM or flash to RAM, and then afterwards we are playing that song on our speaker. Okay, so then the microprocessor reads those data basically from the non-volatile to volatile, such that it can speed up. And then if necessary, you can also update the memory locations by using the write operation, by storing new information, by overwriting in certain cases. Okay. Then we will go to this slide in the next class. It's already 104. Okay, so we'll go to the further classification and how the memory is actually communicated with the microcontroller. So we'll start from the next class. Okay, so if you have any question, you can ask me.
Sir, you said that in the memory, every piece is byte addressable.
Yeah.
Sir, so in the RISC instruction, we can access each byte of the 24-bit instruction, right?
In CISC, we have to access one after another. That means one at a time, one 8-bit, then second 8-bit, then third 8-bit. So for move source destination, we need 3 bytes. For RISC instruction, the memory organization is different. That means the memory chip is also different for RISC instructions. So for that to happen, one location consists of more than 8 bits, like 24 bits. So you are just doing one time read, you are all getting 24-bit data in RISC. Okay, so that means you are reading 8-bit, but 3 8-bits, one all at a time in RISC processor. So that means in one location only it is reading, but the same location consists of 24 bits instead of 8 bits. So that means you are reading 24 bits together. So that is possible. Even 32 bits are possible. 64 bits simultaneous read is also possible, assuming your memory is organized in that way. If your memory is not organized in 24-bit side-by-side way, your processor is helpless. Your processor cannot read them simultaneously. Then your processor, even if it is RISC, it will have to go one by one byte at a time. So that's why I was showing the digital calculator connection. So your connections, your supporting chips outside the microcontroller should also have their matching with each other. So that matching is very important. So unless they are matched in data bus width. So in 8051 in that diagram, if you look at it once again very quickly. So D0 to D7 or D7 to D0, whichever way you talk about it. So there are 8 bits data lines. This RAM chip is also 8-bit data line, right? D0 to D7 or whichever way, D7 to D0. There are 8 bits for this RAM chip. There are 8 bits for this LCD chip or LCD module. So that means everywhere 8 is common for the data bus. So microcontroller is supporting 8 bits, memory is supporting 8 bits, LCD is also supporting 8 bits. So this is the kind of matching that you have to do. Assume this microcontroller is a RISC processor where you have 24 bits data. So your memory should also have 24 bits data, D23 to D0 instead of this 7 to 0. D23. So then you also have need D23 to D0. So you need 24 bits in that case, if it is a RISC. Although this is not a RISC, this is a CISC processor. So there should be a matching. That is the most important or one of the most important considerations while designing your computer system, while looking at speed, RISC processor, all the memory selection happens. Okay, so I'll take the attendance quickly. Stop sharing. Stop sharing. Just wait a moment. I'll take the attendance. Okay, so I've downloaded the attendance. Okay, you can, all of you can leave now. So
Thank you, sir.
Yeah, welcome.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Sir.